Here is the review from the previous lecture. We talked about several bonds that are available in material, but here we are mostly focused on metallic bond, and this is the type of bond we have in metallic. We have a electron cloud in the solid material, and the electron is going to be shared between all atoms. That's why we have high electrical conductivity in metal materials. And then we discussed the different type of crystal structure are available in material, solid material, mostly metal. And this is the BCC. It means body center cube. We have one atom inside the unit cell. The unit cell, we said that the smallest repeating cell is called unit cell, and every material is consists of many of these unit cell, and all of them are the same. And for the BCC, we have one atom on a corner, and one so 8 atoms totally on the corner are located, and we have one atom inside the unit cell. And then we discussed the phase FCC crystal structure, where we still have one atom on the corner, but here, instead of having one atom in the center of the unit cell, we have atom located on the face. So one atom here, one atom on the top side, one atom on here. Same thing on the rear part of this unit cell. Totally, if you have 6 atom times half. And then we have HCP, which is not cube anymore. So we have 3 planes of atoms stacked on top of each other. Also, we discussed the polymorphism concept, which is a property of a characteristic of some material that shows more than one crystal structure. For example, low carbon steel or Fe, iron, pure iron. We have BCC structure and FCC structure. It's not one crystal structure. We have more than one crystal structure. Up to from room temperature up to 900 degree Celsius, we have BCC structure. But after that, above this temperature, iron transforms to FCC structure. Then around this temperature, about 1400 degrees Celsius, it will transform to BCC structure. This is a characteristic that we use in heat treatment to change material, the mechanical property of low carbon steel or other type of steel, and it can be beneficial. Also, we discussed single crystal and polycrystalline material. If we have a material that has all the unit cell, the BCC, we mentioned BCC, right, and FCC. If all of them, they are in the same way, in the same direction. For example, this is showing the unit cell. All of them are in the same direction. So in that case, we have only one grain, and it's called single crystal. And if you don't have this type of behavior, if the grains or the unit cell, they have a random orientation like this one during solidification, it can happen, and you have multiple many grain that form during cooling process. Then we have polycrystalline. remember that single crystal is anisotropic. It means it has a property, mechanical property, different in different direction. So the property are not similar in the all directions. But the polycrystalline, they have normally they have the same property in all directions. In, for example, X, Y, Z, you see the same behavior, mechanical property. We have very few cases that we use, pure metals. Most often in the industry, we use alloys, and alloys are a mix of alloying elements with a pure metal. If you want to understand, the alloys, their properties, we need to understand, the phase diagram, microstructure of alloys, the solid solution, different type of solid solution. We discussed this concept in this lecture as much as possible. And then alloys, as you see, are divided into ferrous material and non-ferrous. Ferrous material are those that we have iron as a base metal, and non-ferrous those material that we don't have iron. So this is Fe. This is without Fe, aluminum, copper, other material. And mechanical property like ductility, strength, the Young modulus, all of these property depends on the alloying element. The composition is one thing that affects the mechanical property. Also the manufacturing processes, the manufacturing process of the product can change the mechanical property. So for example, how fast you're cooling the part. If it is as I said before in the previous lecture, if we cool a metal so fast, we won't have enough time to create large grains. So the grains are going to be smaller. If you have a smaller grain, the strength goes up. This is one example. How the cooling rate, how the manufacturing processes can affect the mechanical property. Also, some of the pure metals are very valuable, but in the engineer application, we use alloys because the pure metal does not have the required mechanical properties, so we add alloying element to improve their properties. And we have two main categories for alloys. One is solid solution, and the second one is intermediate phases. And in the alloys, you should keep that in mind. In alloy, we have one element that has to be metallic. We discuss this solid solution and intermediate phases later on this lecture. Understanding phase diagram is extremely important because there is a strong correlation between microstructure. As I said before, structure can be grain, whether it's small or whether it's large, and other microstructure behavior. We have strong correlation between microstructure and mechanical property. So we can understand this property by looking at phase diagrams. And what we can get from the phase diagram is melting, casting, crystallization, at what temperature material start crystallization, form grain formation, or what are the number of phases, how many phases we have, and what are the their proportion, and how the grains are arranged. And the microstructure depends on the alloying element, concentration, heat treatment, and heat treatment means temperature and the rate of cooling. What is phase? Phase is a separate and identifiable state of matter, and this can be available for both crystalline and non-crystalline material. And also we can consider every pure material to be a phase. So solid, if you have one material, for example water, in solid format, in solid state, it's one phase. If you have liquid of the water, then it is another phase. If it is a vapor, then we have a separate different phase. So if you have all these three phases, for example, you have water in liquid form, and then you have ice, then you have gas, all of them, even they have the same composition but their state are different, we can say their phase are different. So this is water, one phase in liquid form. This is solid of water, which is ice. This is the second phase, and this is a vapor, and that is third phase. Here is another example: sugar and water. We have a cup of water, right? The water is one phase, and then we have sugar cube. It's in solid form and different composition. It gives you the second phase, and then we have this another cup of water that we want to add sugar into this cup. So we're going to mix sugar with the water. The sugar should be some amount that it's going to be solved completely. Then this mixture gives you a unique phase, and it's a solution, right? A unique phase which is called syrup. So this is in terms of composition, this is new, and also in terms of phase, it is different from this one and this material. Probably you have seen phase diagram for water. This is a very well-known example for water, where we have pressure, temperature. As you see here, this is temperature. At different temperature and pressure, we have different state of water. Here, this is a triple point. Under this air line, we have all vapor at different pressure and different temperature. This area, and this area we have liquid, and at a low temperature and high pressure we have solid water, which is ice. So, and this type of phase diagram is called one component or unary phase diagram. And if we have multiple materials, so it's going to be a little complicated. But what happens, we have here temperature versus pressure. So in the two component, we remove pressure. We consider that phase diagram is going to be taking place at 1 atmosphere, one constant pressure. So in that way you can make the phase diagram a little simpler. Equilibrium is another essential concept that we should be aware of in this course. In the thermodynamic, you learn quantity called free energy. In brief, free energy is a function of internal energy of a system, and also randomness or disorder of atoms or molecule, which is called entropy. A system is in equilibrium if the free energy is at minimum under some specified combination of temperature, pressure, and composition. If that happens, then a characteristic of the system do not change with time. So we call the system is stable. Solubility limit is another terminology and another concept that we need to know when we are dealing with the solid solution of alloys. There is a maximum concentration of solute atoms that may dissolve in solvent to form a solid solution, which is called solubility limit. What is solute and what is solvent? You have a cup of water, again, that water and sugar example. The water is a solvent, right? And then we have solute atom, which is sugar. You add sugar, then the sugar is going to be dissolved in this water. If you keep adding sugar, the sugar is not going to be dissolved. Then the sugar actually is going to be saturated in the water. After some time, the sugar is going to settle on the bottom of the beaker or the cup. And then this is a new phase. That phase, so you have a phase here called syrup. And this is sugar. And this phase is completely separate from this phase. So the water has some solubility limit. When you reach that solubility limit, then excesses of that solute is not going to be used to be dissolved in that solvent. Same thing happened in the sugar and water. And we use the same concept for metal as well. But is there a way to increase the solubility limit of the water so we can add more sugar into the water? Yes, it is possible. One way is to increase temperature. Look at this graph. This axis is temperature and this axis is the composition. So when the room temperature we are working at the room temperature, we can add up to 65% sugar into the water. As you go here, the amount of sugar increases and the amount of water decreases, right? So, but as you see, temperature goes up, you increase the temperature, solubility limit goes this way. It means you can add the solubility limit goes higher, so you can add more sugar into that water. But up to 100 degrees Celsius, which is the vapor temperature, we have this much solubility. I want you to pay attention to this part. What is the phases that are available at this temperature, 20 degrees Celsius and 65? It depends, if you are here, you have only syrup. If you go this way, you have syrup, sugar, and the mixture of sugar and water. But the interesting point is here, if you go the other way, if you have a composition like this, you will have liquid. Liquid is going to be the syrup, and the solid sugar, which is settled on the bottom of the beaker. Similar to syrup example, we can have equilibrium state with the solid material. Here we have copper and nickel, two solid materials that are mixed together. As you see, for example, here these two elements, copper and nickel, are mixed, and we have this pattern. Look at the mixture of these two atoms, two elements, and that because this is unique, and that gives you phase A. But in some cases, the pattern, the mixture can be different. Look at this type of arrangement and compare it with this arrangement. So this arrangement is different from this. So then this is another phase, and it's called phase B. So here are some of the important terms in the solid solution. In the solid solution, similar to the liquid solution, we have solute and solvent. The solute is the minor element, such as salt, sugar, that is going to be added to solvent, and the solvent is the major element, such as water. We have two types of solid solutions. One is called the substitutional solid solution. This one, where we have both atoms in the same size, and we have solvent. This is solvent atoms, and this is solute. One example can be brass. In brass alloy, as you know, it's an alloy, a mix of zinc and copper, right? Sorry for my bad spelling because I'm using my mouse. Here, the zinc is going to be the solute, this one, and copper is going to be solvent. The next one is interstitial solid solution. If the size of solid atom is much smaller than that of solvent atom. A good example is steel. In steel, we have iron, Fe, and this is small particles or carbon. The size of iron, the size of iron atoms is 0.12524, I think, nanometer, and carbon atom is about 0.078 nanometer. So this is way smaller than the iron atom size. Similar to the example I mentioned before, the water and sugar, we have a solubility limit for solid material, and when the amount of dissolving element in the alloy exceed the solid solubility limit, then a second phase forms in the alloy, and the term intermediate phase is used to describe that excess alloy or excess elements, and its composition is going to be between the two pure elements that are mixed together. In the structure, crystal structure is also different from the pure metal. We have two types of intermediate phases. One is a metallic compound, where we have one metal and one non-metal, such as Fe3C, is cementite, which is a common compound in steel, carbon steel, and for the steel we show St. And then we have intermetallic compound, where we have two metals that they form a new compound, and the property are unique compared to the two pure metal. One example here is magnesium plumbide, or aluminite titanium. See, aluminite titanium, or aluminite nickel, or aluminite iron. They should have three over there, and they are brittle. They are brittle. They are hard, and they have high melting point temperature, Tm, very high. Their strength is high as well. So these are some of the characteristics of intermetallic compounds. Here we have a phase diagram for copper and nickel. It's a very well-known system, and it has two components, as you see, copper and nickel. And because we have two components, it's called a binary system. And we have two variables, as you see here on the bottom. We have composition, which varies from 0 to 100. As you see here, it says weight percent nickel 100. It means at this point we have 0 copper and 100% nickel. As you go this way, then we have 100% copper Cu and 0% nickel. But what about this point? At this point, you have 50% copper and 50% nickel. Okay, so the composition of both changes depending on where you are. And this is the temperature. The temperature was assumed from 1000 degrees Celsius up to 1600. So below this temperature, it was not area of interest. We have some area here, three separate area. As you see here, in this blue region, we have a complete solution of nickel and copper. It's called FCC solid solution. And on this point, once we have a copper, 100% copper, so the melting temperature of that material is going to be exactly the same as the melting temperature of pure copper, right? But and also the same thing here is valid for nickel. This is the melting temperature of the nickel. After that temperature, we have liquid. So above this temperature, we have liquid of copper, but below it is solid. But once you add some nickel into this copper material, the melting temperature increases. So this is the melting point. Actually, we have the melting. This is the liquid point line that represent beyond this point, the material is going to be completely in a liquid form state. But above this point, this line, we have solution of copper and nickel plus some excess of material. Unique phase, which is alpha. Alpha is present below the solidus point. Below this point, below this line, we have all solid, and above this line we have liquid and some solid material. Okay, so later on I'm going to show you how can we determine the amount of liquid in this region. For example, if we are dealing here, at this portion, how much liquid we have, how much alpha we have at certain temperature, at certain composition. Here in this slide, I'm going to show you the effect of temperature and composition in the phase diagram of the copper nickel system. As you see, if we change T, the phase will change. Here, if we are at 40% of nickel, it means you have 60% copper, right? So the combination, the sum of these two numbers has to be 100%. When you are at this point, what phase you have? You have only phase alpha. Alpha is the, for example, solid material, FCC. When you mix, copper and nickel, you get FCC structure. You remember, you don't need to memorize, this behavior, but just for your information. One on the face, one on the corner, right? So as temperature goes up, we reach the melting point, and we are in the liquid form, liquid state, from A to B. And what happens if we go to a point D? In D, we have alpha plus liquid. If we have the phase diagram of a system, we can find out what phases we have based on the temperature and composition. For example, this is a copper nickel phase diagram, and then we have one point. The point is 1100 degrees Celsius. We can draw a line, horizontal line, and then it says 60% nickel. So we plot a vertical line, and then we, as you see, these two lines cross at this point. So that is the point of interest. And at that point, as you see, it's in this area, and this area is the solid area. So we have only one phase, right? This is one phase. But if we are in 1250, we draw one line, and the composition is, excuse me, let me fix this one, and the composition is, the composition is this. So we are in this gray area. The gray area, we have both liquid and alpha. Alpha is a solid material. So we have two phases. The second rule, we can find the composition of each phase based on the temperature and the composition. Here we have, a point A at temperature 1320 degrees Celsius. What is the phase we have there? As you see here, it's in the green area, and the green area is called liquid for this system. Okay, now keep that in mind. This is for nickel copper nickel. So this, if the phase, if you are talking about this system at this temperature, we have only no liquid. And the composition, what is the composition of that liquid? If you draw one vertical line until you cross this horizontal axis, you can find the composition. The composition will be, as you see, 35% weight percent nickel and 65% weight percent copper. But in the next point, which is point D, here again we have a solid phase, and the composition again is 35% nickel and 65% copper. How about we are in this region? If we are in that region, if we have both alpha and no liquid, alpha is a solid material, L is the liquid material. So this is a little tricky. If you are here, the composition is not 35%. You have to draw a horizontal line. So this horizontal line has to cross this solidus, this liquidus, and this solidus line. When you cross that two lines, for example, solidus line, and then you need to draw another line, vertical line, to find the composition of that solidus, to find the composition of that alpha. Here, as you see, the composition of that alpha is 43% nickel. And then we have to repeat it for the liquid material. And then we come here, we draw a vertical line. Then we cross this horizontal axis. Horizontal axis gives us 32% weight percent, 32 weight percent nickel, or 68% copper. So this is the way we can find the composition of multiple phases if you have multiple phases, right? In this region, we were dealing with one phase, so you just simply draw one vertical line to find the composition of the material. Same thing in this region, the liquid. But if you are in this gray region, you are dealing with multiple material. For our case, this is binary system. We are talking about about two components. Then you just need to draw a horizontal line to find the solidus point and the liquidus point, and then draw a vertical line to find out the composition of those two phases, liquid and solid material. So I showed you how can we determine the composition of material, the composition of component in different region. If you are in the liquid region, if you are in the gray area, or that you have multiple components, or you are in the again solid region. But how can we determine the amount of each phase? Okay, at the liquid region, if you are in the liquid, for example, point A, how much liquid we have there? Almost all of them is going to be liquid, so 100% weight percent liquid. So how much solid we have there? It's a zero solid, right? Only liquid. But if we are looking at point D is here. Point D, we have 100% solid, no liquid material. So it's 100% only solid material. But here we are in the gray area, and we have two material, liquid and solid material, and we want to find out how much of liquid we have there and how much again, this is not composition, this is the amount of each phase in the material, in that point of interest. For example, this is the point of interest. They told us at this temperature and at this composition, find out how much phase, how much of solid phase and how much of liquid phase we have at that point. Okay, so we have to use a tie line. So again, we have to draw a line, horizontal line, to cross this, liquid this line and this solid line, and we have to measure, or we have to calculate these two area here, and the total. Okay, so the total, for example, total is going to be the denominator for this equation. If you want to find out the portion of the liquid, so you subtract this number 43 minus 32, right? And it's going to be the same, it's going to be used for the other equation. But here we have 43 minus 32, and then we want to use this portion for the liquid part. Remember, if you're dealing with the liquid, you have to use the other portion. So 43 minus 35, and that gives you 73% liquid. It means that you are closer to the liquid line, right? And we do the same thing for the alpha. So the denominator is going to be the same, 43 32, and numerator is going to be this portion here, 35 minus 32, 35 minus 32, that gives you 27%. It means you're further away from the solidus line. Okay, this is the the technique is called tie line. This is the one way to calculate the amount of each phase when you have multiple phases at the point of interest.